Okay, let's look at logistic regression. And this logistic regression is what? We're going to make the comparison to logistic regression model to simple linear regression model, okay? Although it can compare to what? Multiple regression model, since we did not go deep enough to make the comparison. So I compare to what? To simple linear regression model, okay? Now look at here. The simple linear regression model is appropriate for relating a quantitative variable, y, to a quantitative variable x, okay, predictor x. In our previous mentioned model is y equal to beta naught plus beta 1 x plus epsilon. And our epsilon is what? Normally distributed with mean equal to 0 and sigma squared. Okay, I think you are all familiar with this model now. In some real-life application, however, the response variable can be a two-level categorical variable we call binary variable with possible value 1 or 0. Okay, or we call this is Bernoulli, right? Corresponding to success and failure. If success, we call as y equal to 1, but its failure, we call y equal to 0. Y equal to 1 means what? You see one success. Y equal to 0, you see what? You see failure, you see what? 0 success, okay? So that's 1 and 0. When the response variable has only two possible values, it is desirable to have a model that predicts a value either 0 or 1, or as a probability score that ranges between 0 and 1. Logistic regression can be used to model and solve such problems. In logistic regression, we get a probability score that reflects the probability of success or occurrence of that event, okay? Now, let's quickly look at example 1, okay? What kind of application we can have in the real life application. Example 1. Example 1. Kyphosis refers to severe forward flexion of spine following collective spinal surgery. A study carried out to determine risk factor for kyphosis reported to accompanying age measured by what? How many months old, okay? Or how many months for 40 subjects at the time of operation. The first 18 subjects did have kyphosis and remaining 22 did not, okay? In this kind of question, if a subject has kyphosis problem, we consider that as a success, okay? Recorded by 1, because this is what? Event of our interest, okay? We try to observe an event, and if you see that event, the occurrence of that event, we call one success. So this is recorded as what? 1, 1, 1, 1. And if a particular subject don't have that problem, we record as 0, 0. So in this kind of coding, how many subjects we coded by 1? 18. And this 22, we coded by 0, okay? Coded by 0. And this is our y. This is y, okay? And this one is x. Okay, x1, x2, and so on. Is that clear? This is month, age. And y is, you see a subject has kyphosis or not. If you see it, you code it by 1. If you don't see it, code it by 0. This is a coding. Example 2. The following data resulted from a study commissioned by a large management consulting company to investigate the relationship between amount of job experience, unit use, how many months working experience for a junior consultant, and the likelihood of the consulting being able to perform a certain complex task. Okay? So let's check here. The first junior manager, his or her working experience, 8 months. Okay? 8 months. This is my X1. Okay? And this subject, okay, this consultant, successfully what? Complete the task. Success, this is Y1. Okay? And this is X2, Y2. As you can see, up to here, these are what? The junior consultants successfully complete a certain what? Complex task. And this is how many months what? Their working experience. Okay? And the remaining for those what? Junior consultant who are unable to complete the task. And this is his or her working experience. Okay? If you compare with simple linear regression model, okay, the data set X1, Y1, X2, Y2, all the way up to what? Xn, Yn. If you plot the data, what you're going to see, X and Y. You're going to see a football share scatter plot, okay? And then you decided to fit it, the data set with a line. You fitted the data set with a line, okay? But compare a data set like this. Okay, the data set X is working experience. And Y is successful or not. Okay, successful, you code it by what? By 1. Suppose this is 20 months old. This is 40 months old. Look at 1, 2, 3, 4, 5, this data set. A junior consultant, working experience is 20 months, and that is success, okay? Say this line is Y equal to 1, and this line here is Y equal to 0. This is Y equal to 0. 20 months of working experience. We code it here. It's a success. So suppose I put a circle here, okay? And 21 also success. So you put a lot of circle here. I just put it randomly, don't follow the data, okay? So you know what's going on. And on the other hand, those junior consultant, failure. They are the consultants with less working experience. So if my picture look like this, okay? You're gonna see what? More success when X is bigger, less success when X is smaller. This kind of data set. So from the data set, you can tell this is a data or the model. You can use what? To make prediction, okay? In logistic regression, we get a probability score that reflects the probability of the success of the events. Say we denote it by Px. What's Px? Well, it's a probability of getting success given the working experience is X, okay? Or we denote it by probability Y equal to 1 given X equal to X. Look at this probability. How are we going to interpret this probability? Given a junior consultant, his or her working experience is X month. How likely he or she will successfully complete the task? Okay, that's this notation stands for. And know that Px is a probability and must be between what? 0 and 1. Okay, now to model this kind of question, we cannot use what? Usual least square regression model, okay, for a couple reasons. If you run simple linear regression model, okay, if you run simple linear regression model, say y equal to beta naught plus beta 1 x. Given x, you want to predict y. In a simple linear regression model, okay, in a simple linear regression model, when you plug in x, you want to predict y. Okay, so I put a y hat here. Now, x, if the x is what? A continuous variable. Y also continuous. There is no way you can restrict y just between what? You cannot restrict y between 0 and 1. That is a problem. But that problem can be solved if we find what? Find a nonlinear transformation, okay? And the function we're going to use for that nonlinear transformation is called logic function, a logic function, okay? So let's look at the logic function. A function that has been found quite useful in many applications is a logic function, okay? So this is a logic function, and let me write it down for you, okay? F of x, or I say ft, equal to e to the power t plus e to the power t over 1 plus e to the power t, okay? This function will look like this, okay? Okay, and this point here is y equal to 1/2. And this is t equal to 0. Okay, this is called a logic function. Okay, a logic function. And the possible value of y can only be what? This is y. can only between 0 and 1, okay? Now, if I change to what? Minus, minus, the picture just flip it over, okay? This is a graph or logic function for a particular value of beta naught and beta 1. So we make a transformation on t, okay? And transform to what? Well, later you can treat beta naught plus beta 1 x, okay? You can put this as t. Think about it this way, okay? This is a graph or logic function for particular value of beta naught and beta 1 with beta 1 greater than 0, okay? That means beta 1 and what you want to study, they have a positive association, okay? As x increase, the probability of success also increase. If beta 1 less than 0, then as I mentioned, is what? Flip it over, okay? When x increase, the y decrease, okay? And for beta 1 less than 0, the success probability will be decreasing function of x, okay?